Now, see here, this is a chemical cell. This is here we have used here the beaker here, in which electrolyte is placed. Inside the electrolytes, two electrodes are here, and these two electrodes, P is here the positive and N is here negative electrodes. Now, this is the point A and B adjacent to just electrode P here, and this is adjacent to the electrode N negative electrode. Externally, one resistance R is connected across the ends of these two electrodes P and N. Now, see here the potential at P is relative to this point A is, suppose this is here V plus, and potential at N relative to the point B, that is just adjacent to the electrolyte, is here V minus. So, this is here the negative potential and this is here positive potential. So, when no current is flowing through this circuit, say the potential difference between these two P and N, we can write V plus minus minus V minus, that will be here V plus plus V minus, which is greater than 0. And this is known as actually EMF of, this is the symbol for EMF, EMF of the cell, that is V plus plus V minus. So, actually EMF of the cell is the maximum potential difference between two electrodes when no current is drawn from the cell. So, when the no current is being drawn from the cell, then also this is known as EMF of the cell. EMF has got non-electrostatic origin. Actually, EMF is something, it is not actually force, as its full form is electromotive force, but actually not, it is a force. It is something which actually motivates the charges to move, and this is coming here due to chemical reactions inside the cell. And basically EMF of the cell depends on the concentration of the electrolytes, or you can say also here the nature of the electrolytes. And now there is one more concept, that is called internal resistance. So, these two electrodes are dipped in the electrolytes. So, the resistance offered by the electrolytes and the electrode is known as internal resistance. We represent internal resistance by here small r. So, symbol for internal resistance we take here small r. So, just now we have seen the internal resistance offered by the electrolyte and electrodes, and now see the internal resistance depend on actually the distance between two electrodes, the nature of the electrolytes and temperature and area of the electrodes dipped in the electrolyte. Now, see here, suppose a chemical cell has got internal resistance R. So, we can represent like this, suppose this is a chemical cell and it has got internal resistance R. So, we can write here R below just this is R. So, this cell has got EMF this here and internal resistance R. Now, these are the two terminals of the cell here. Externally, now we connect here the resistance R like this. Now, when the resistance R is connected, current is start flowing from this side to this side. But here outside current is going here positive to negative, but inside the cell current is going negative to positive. So, here we can write the total current I is equal to actually EMF upon R plus R. This is the symbol for EMF. And we can also write IR plus IR is equal to this EMF. We can write IR is equal to EMF minus IR. This IR is the potential difference across these two ends. We can take suppose this point A, this point B. So, this is the potential difference between, or the terminal potential difference also we call it. This is the terminal potential difference between the two electrodes of the cell when the current is flowing. So, we can write this is your V is equal to EMF minus IR. So, this is the relation between actually here, relation between terminal potential difference, EMF and current and internal resistance. Now, see here, suppose if I is 0. So, if you are taking here I is equal to 0, then what will you be getting? V is equal to EMF. It means the maximum potential difference, maximum terminal potential difference of the cell is equal to EMF when no current is drawn from the circuit. it means you can say no, that is the circuit is open, that means no current is drawn from the cell. So, when the current is being drawn from the cell, then potential difference is equal to EMF minus IR. It means V terminal potential difference is less than EMF when the current is being drawn from the cell. Suppose if the current is not being drawn from the cell or the cell is being charged, then we can write V is equal to EMF plus IR, and in this case V is greater than EMF. So, actually when the cell is being charged by putting any external source, then terminal potential difference is greater than the EMF of the cell, otherwise terminal potential difference is less than the EMF of the cell. So, now we can calculate expression for internal resistance also. So, we can take internal resistance, we know the formula V is equal to EMF minus IR, that is V is equal to EMF minus IR. So, we can write IR is equal to V minus EMF, R is equal to V minus EMF upon I. So, R is equal to V minus EMF upon V into here, just to change here, we can write here IR is equal to EMF minus V. So, I is equal to EMF minus V upon R. So, here we have to calculate R. So, EMF minus V upon I, and here we can write EMF minus V upon V, that is R. So, this is expression for the internal resistance, EMF minus V upon V into R.